Somewhere in the world's oceans, around 800 feet down, you'll find one of the most dangerous vessels ever made, the nuclear submarine. Only 6 nations are confirmed to have them: the US, UK, Russia, France, India and China. Unlike regular submarines, nuclear ones are truly enormous. For example, the Ohio class, operated by the US, is 170 metres in length with a displacement of nearly 19,000 tonnes. To put that into perspective, the Statue of Liberty is only 93 metres tall. On the surface, submarines are very similar to all other ships. As they slip beneath the waves, however, there are some very interesting and fascinating differences that we need to know about. We were looking at the differences between ships and submarines. Firstly, most obviously, there are huge implications in terms of buoyancy and stability. With a ship, you just need to make sure the underwater part of your vessel displaces enough water to provide buoyancy to keep it afloat. Submarines, of course, are a little different. On the surface, just like a ship, the hull needs to displace enough water to provide positive buoyancy, but it also needs to be able to sink, so you need to be able to increase its displacement to make it weigh more than the water it displaces. It's actually quite simple. You just flood some ballast tanks, making the vessel heavier and less buoyant, basically so that it sinks. That's great for going down, but then when you're deep enough you need to be neutrally buoyant instead. You want the submarine to weigh the same as the water it displaces, so that it neither floats nor sinks. Again, it's quite simple, you just pump out a little ballast water using compressed air from cylinders. Done precisely enough, you can make the submarine weigh the exact same as the water it displaces, making it neutrally buoyant. So, that deals with the buoyancy, but what about stability? After all, a submarine still needs to remain upright when underwater. Remember how a ship uses form stability to stay upright? This just means that the shape or form of the hull provides a righting force whenever the ship leans over slightly. The underwater shape changes, shifting the centre of buoyancy, separating the force vectors, creating a moment to right the ship. This is how, counterintuitively, the centre of gravity can be above the centre of buoyancy. A submarine, however, can't do that. When it's fully submerged, its underwater shape remains constant no matter how far it leans over. Its centre of buoyancy doesn't move. Instead, you have to rely on keeping the centre of gravity below the centre of buoyancy. Your stability is provided by the force of gravity and the force of buoyancy pulling in opposite directions. Underwater, it's easy because you just make sure the heavy things are placed low down, but on the surface it can be a little harder. Think about it. As the hull emerges from the water, the centre of buoyancy drops lower down because it's just the centre of the underwater volume. If you let it drop too low, it might go below the centre of gravity and the submarine would just flop over. This is why submarines appear to float really low in the water. They need to keep the centre of buoyancy above the centre of gravity. So, we've now dealt with buoyancy and stability, but what about navigation? We already said that on the surface submarines can do the same as any other vessel. You can take bearings of navigational features like lights or headlands, you could use a radar to measure distances, or you can just use GPS to get an immediate satellite fix. As soon as you disappear below the surface, however, none of that is possible. Instead, you need to try and track your movements since your last known fix. The system that does this is known as an inertial navigation system. It uses a collection of accelerometers and gyroscopes to calculate the vessel's movements and keep track of its location with reference to the last known position. Obviously, over time, positional accuracy reduces, though if you're in the middle of an ocean with nothing for hundreds of miles around, it really doesn't matter. Your only other option might be to use sonar or visual markers to try and find your way. Of course, visual markers are fairly useless underwater because it's so dark you can't actually see anything. This is why recently the USS Connecticut apparently ran into an underwater mountain. They just didn't see it. So what about sonar? Well, that would immediately give away your position, so that's actually a non-starter too if you want to operate unseen, as most military submarines do. Of course, if we're saying that sonar is so loud that it gives away your position, what about the submarine's engines? Well, this is another interesting fact about submarines. They're actually powered by electric motors, so that they can run almost silently. I know you always hear about either diesel or nuclear submarines, but that's only referencing the source of the electricity. Diesel submarines come to the surface to run their diesel generators and charge their batteries. Nuclear submarines have a mini nuclear power station on board to continuously generate that power instead. The electrical power drives not only the propulsion electric motors, but also the rest of the submarine systems. I'm talking about everything, including the navigation systems, the freshwater generators, and even the oxygen generators. Remember, to stay submerged for extended periods, the submarine needs to be able to generate its own fresh air for the crew to breathe. You can use scrubbers to remove carbon dioxide, but you also need to add oxygen. Of course, the vessel itself actually has a limitless supply of oxygen surrounding it. It's just that it's bonded with hydrogen in the form of water. To separate it out, you can use a process called electrolysis. Just pass an electrical current through two electrodes submerged in water, H2O, and you will get oxygen produced at one and hydrogen produced at the other. Of course, as with everything, it's not quite as simple as that. If you attempt electrolysis with seawater, you'll actually produce chlorine gas because of the salt or sodium chloride in the seawater. You don't need me to tell you how dangerous chlorine gas would be. So, you need to make sure your oxygen generators are fed with fresh water. Fortunately, the submarine needs to have freshwater generators for drinking water anyway, so you can just use some of that for electrolysis as well. There are plenty of technologies that can create fresh water from seawater. Evaporators or reverse osmosis systems are the most common, or you could simply have a load of fresh water in storage tanks. With a large enough fuel supply, like a nuclear reactor, submarines can actually generate almost everything needed to sustain life. The only thing it can't make is food, which is why the food supply on board is actually the governing factor when it comes to extended deployments. And that brings us to the end of today's video.